Welcome to Conceptual Physics at Delaware Tech, Chapter 21, Musical Sounds. So in the last unit, we discussed sound in general. In this unit, we're going to talk about sound as it relates to musical sounds. So first, we'll do a quick discussion on noise and music, and then we'll talk what musical sounds are, and we'll talk about some of the characteristics of musical sound, pitch, sound intensity and loudness, and quality of sound, also known as timbre, sometimes referred to as the color of the sound, the tone of the sound. We'll talk about how musical instruments make different quality sounds, even if they're playing the same musical notes. And then we'll talk about something called Fourier analysis or Fourier transform analysis that analyzes complex waveforms and turns them into a collection of simple waveforms. And then we'll talk about some of the digital devices that are out there today, including the DVDs, the digital versatile discs that can store enormous quantities of information, sometimes in the form of music, sometimes movies, sometimes computer data. All right, so music and noise and music. All right, so what people call noise and what people call music, that's a subjective term, but to a physicist, noise refers to irregular vibrations of the eardrum, your eardrum, produced by irregular vibrations in the surrounding, a jumble of wavelengths and amplitudes. And perfect white noise is when you have a completely random collection of all frequencies within the human hearing range, and the intensity is all roughly. And I can give you an example of that. On my phone, I have a number of different white noise type sounds. Here's what white noise would sound like. And you'll notice the human ear picks up higher frequencies a little better than lower frequencies. So there's another version of white noise called brown noise where they make the lower pitch sounds, the lower frequency sounds a little higher, and the higher frequency sounds, the higher pitch sounds a little lower, kind of even out what our hearing is good at detecting. So it sounds more like that. I'll go back to the white noise, and here's the brown noise. You can hear it. But these are in the same realm of random frequencies, a collection of all frequencies simultaneously being played, just with different intensity variations to get these other types of white noise variations. Okay, so music is the art of sound. It has a different character. All types of music have different character. And usually people can recognize music from non-music based on the character of the sound. It tends to have periodic tones, tones that we perceive as musical notes or many musical notes. So below is a pattern of sound wave, and the sound wave, remember, is the compression of the air, in other words, high pressure, followed by the rarefaction of the air, low pressure, high pressure, low pressure, and that is how the wave travels. And there might be variations of that, so there might be variations within the variations, and that gives this complexity of waveform. Now that's presented here as if it's a transverse wave moving up and down, but these are longitudinal waves of compression of air. It's just showing them this way on this type of graph is a much easier way to represent it so that you can see it instead of seeing many particles coming together and particles coming apart. It's hard to visualize sound that way. So we usually represent it as if it was a transverse wave, which it is not. It's a longitudinal wave. All right, so the line that separates music from noise is completely subjective and thin, meaning everybody thinks some forms of music are noise to them and other forms of music are music to them. And I could pick any genre of music, anything from classical music to country music to thrash death metal. There are people that think each of those are beautiful sounding, and there are people that think each of those are noise to them. It's a totally subjective thing, and that is up to the human being. But in terms of physics, when we talk about noise, we're talking about random patterns, both in terms of the frequency and the amplitude, how high, how intense it is, or how low it is in sound as it's varying from the crests to the troughs in that waveform. It might be very narrow amplitude or very high amplitudes. And that variation will produce sounds that we either find pleasant or we don't find pleasant. All right, so musical tone. When we're talking about tone, we're talking about the notes we hear that might be more than one note superimposed on another note. In other words, more than one frequency superimposed on another frequency. But we have several different ways that we characterize musical tones. The first one is pitch. And pitch is directly related to frequency. So frequency is something we can absolutely measure. We can take a device and say, oh, this wave has a frequency of 440 hertz. It vibrates, it goes up and down 440 times per second. That's what a hertz is, all right? But how we perceive that with our ear as being a high pitch, a medium pitch, a low pitch, that is pitch, okay? It's how humans perceive frequency is pitch. That is a subjective term based on that human's experience of the frequency that they're hearing, okay? And so it's determined by the frequency, and specifically it's determined by what we call the fundamental frequency. So if you have a tone that is composed of many waveforms, you'll have a musical instrument might play, say, a middle C on the piano keyboard. They'll play a note, and they'll hit that note, but there won't be just one frequency in there. There's going to be one frequency, one main frequency, but there are also going to be multiples of that frequency. So let's say they hit a relatively low note that had 100 hertz. 100 hertz is pretty low on the piano. And if you hit that, you will also hear undertones of other frequencies right on top of it. You will hear 200 hertz. You will hear 300 hertz. You will hear 400 hertz, all blended together. And each one of those frequency waves, each one of those waves that has a different frequency that's a multiple of the original frequency, the fundamental one, the lowest frequency, well, each of those individual ones we call partials, they all have their own amplitude. In other words, some of them are quiet and some of them are loud. And they add together to form some complex pattern that has a general wave pattern, repeating pattern, that's the same frequency as the lowest frequency, the bottom note. But there's a lot of complexity within the note, so it's not a single tone. It's a multitude of tones together. And the human ear will perceive these, but generally we'll perceive these as the lowest of those tones, the lowest of those frequencies, and that's the one that we will associate with the pitch of a sound, the note, the musical note of a sound. So that lowest frequency is called the fundamental. It's also called the first harmonic, by the way, and we'll talk about that in a little while. Another characteristic that's important in music is the intensity. And the intensity is how much energy is being produced per second for a certain area as the sound is being spread out. And you might say, well, what does that mean? Well, what that means is that is perceived by humans as loudness. Loudness is not something I could take a technological instrument in the lab and say, oh, it's this loud. Loudness is a human subjective perception of the intensity of the sound. And intensity is just calculated directly from the amplitude. The bigger the amplitude, the bigger the intensity. In fact, it's related to the square of the amplitude. So if I had a wave that went up and down in the whole, the amplitude, which is half the width, if I doubled the amplitude, in other words, I made the whole wave twice as high up and down, that wave would produce 4 times the intensity of sound, and we would perceive it as being louder. How much louder is a complex formula, and it's different for every human. The third characteristic of tone I've already hinted at, and that's the quality, also known as the timbre. It's spelled T-I-M-B-R-E, but it's pronounced timbre, not timber. Timbre. Timber is what you say when you cut down a tree. And so the timbre of the sound is really the characteristic of the sound that makes it unique to each human voice or musical instrument. So 2 instruments could play exactly the same note, but they'll sound different. You'll be able to tell the difference. And that is because of the relative intensity of all these other multiple frequencies on top of the fundamental. And these multiple frequencies that are double, triple, quadruple the fundamental frequency are called additional harmonics, and they're also called partials or partial tones. And they each have their own amplitude added to the total, and that's what gives the sound characteristic in one musical instrument. So if I played an A note on an oboe, it's not going to sound like an A note played on a violin or an A note played on a piano, even though they're the exact same note. They're playing the exact same fundamental bottom frequency, low frequency, but they all have different combinations of higher multiples of frequencies sitting on top of that, superimposing to make some complex pattern that has a regular pattern with the same frequency of the fundamental. So it's really dependent on the prominence of these harmonics, these partials, all added together to make this complex pattern that has a general repeating pattern with the same frequency as the lowest frequency, the fundamental. And I'll show you what that looks like when we have graphs later. All right, so pitch is related to the frequency, but it is, again, the way humans detect frequency. We don't have a counter in our brain that says, oh, that's 440 hertz, that's 3,500 hertz, that's 10,000 hertz, that's only 50 hertz. We have a method in our ear to hear, and we can tell the difference between high pitches, which are high frequency, and low pitches, which are low frequency. And people with perfect pitch are much, much better at determining what musical note that matches to, and we know the frequencies for each musical note. But in general, detection of pitch is a human subjective ability. It is not a number we can directly measure. We can measure the frequency and correlate it to a musical note, but pitch is the way we perceive it. But we sometimes use the word pitch to also refer to the musical notes, which we do know a number frequency for. So it's a little confusing, but in general, it's a subjective impression of frequency. So every note has its own pitch, and that's because every note has its own frequency, and people perceive high frequencies as high pitch and low frequencies as low pitch. High frequency means rapid vibration of the air as it hits their ear. Low frequency means slower vibration of the air as it hits our ear. And specifically, when I say vibration, I mean the compressions and rarefactions of air as it's slamming through our ear canal towards our eardrum, setting the rest of the ear anatomy in motion. So musical notes, yes, we have specific letters for our musical notes that do correlate to specific frequencies, but most people will just perceive them as a relative pitch, meaning I know that note is higher than the other note and that one's higher still, or this one's lower. People with perfect pitch, as I said, really can nail down what that note is. There are people with absolute perfect pitch who could tell you exactly what note it is, and there are people with relative perfect pitch, which is usually what happens to people that have pitch as they get older. They can tell the difference in notes very well, but not always exactly what that note is. It's still a remarkable ability nonetheless. And I've seen people that you can actually play, especially young people, you can play as many as 8 notes simultaneously on a piano, and they can tell you the identity of each of the 8 notes, which of course each one correlates to a different frequency. And in the United States, we tend to use the notes A, B, C, D, E, F, G, usually starting from C, to represent the notes. We have what are called the naturals. These are the white keys on the piano, as well as the notes that are in between, called the accidentals. If they're just above the white key, they're called a sharp. If you're looking just below a white key, they're called a flat. They go down in pitch, down in frequency a little bit. But every key on here, black or white, if you go to the next key, it is what we call 1/2 step of tone going up every note. So what we have as an octave would be the notes from A, B, C, D, E, F, G, or it can start from any letter, and then come back to the same letter. That will be 1 octave. And it turns out that 1 octave represents exactly doubling the frequency. So if I start from, say, C4 on a piano, the 4th C on a piano, it has a frequency of 261.63 hertz. That's how many vibrations per second. But if I go 1 octave up higher, so it's still a C tone, it's double the frequency, 523.25 hertz. And each time you go to the next C, it's double. But I could pick any note on this scale and go to the next version of that note. I start with B flat and go to the next B flat. It is double. And if you're wondering how much do they go up by each individual note, if you go up from one key to the very next key, whether it's white or black, white, so it's, white, black, white, black, white, white, black, white, black, white, white, back to, so that's the pattern it does. Every one of those is a half step. They're even half steps. And it turns out in terms of frequency, each next key, black or white, is about roughly 6% higher in frequency than the previous key. Well, if you do that 6% increase, 12 increases, in other words, a full octave, if you have 6% increase, 6% increase, and you do that 12 times, you will end up with 100% increase. In other words, you doubled the frequency. And so it all works out here. All right, so a piano keyboard actually has 7 octaves, a little more than 7 octaves of range. So you're doubling the frequency a total of 6 times or more on a piano keyboard. And so the keyboard consists of 88 keys. I'm sure you've heard 88, that's the number of keys on a keyboard. 52 of them are white keys. The naturals, 36 are the sharps and flats, the black keys. But they're all evenly spaced half steps, white and black keys going up. In Europe, they tend to favor a different system. Instead of C, D, E, F, G, A, B, they use Do, Re, Mi, Fa, Sol, La, Ti. That's called the solfege system. Do corresponds to the C note, Re to the D, etc., etc. So pitch, as I mentioned, pitch is our subjective impression of changing frequency. So when you have a vibrating source that's changing frequency, you perceive it as changing pitch. If the frequency gets lower, the wavelength is getting longer. So frequency and wavelength are going to be inversely proportional if the speed of sound is kept constant. And if you're not moving the piano anywhere, the speed of sound for all the notes is roughly the same in the air. And so high frequency sounds shown in the top here have short wavelengths. Low frequency sounds have longer wavelengths. Wavelength is the lambda, that Greek letter that kind of looks like a squiggle with a line coming off the squiggle. That's a lambda. That stands for wavelength. So high-pitched sounds used in music are most often less than 4,000 hertz. In other words, humans, we can hear between 20 hertz, which is 20 hertz would be about 3, maybe 4 keys below the bottom key of a piano keyboard. You wouldn't be able to hear lower than that. And 20,000 hertz is much further up on a keyboard, past the keyboard. If you remember back on the piano that I just showed you, the top note on the piano is just above 4,000 hertz. We can hear up to 20,000 hertz when we're young and we still have perfectly good ears. As we get older, and when I say older, I mean anything above age 25, we start losing our high frequency end. We might lose a little bit of the low frequency, but it's much more obvious with the high frequency range. And most young people can hear close to 20,000 hertz. Some can even hear higher than that. Dogs and many other animals can hear above the range we can hear, into the ultrasonic, the sounds that are beyond the sound range that we can hear. So this 20 to 20,000 hertz range is the human range of hearing. Below 20, we call the infrasonic, below the sound we can hear. And above 20,000, we call that ultrasonic or ultrasound. That's beyond the frequencies that we can hear. Dogs can hear above 20,000 hertz. Bats and dolphins use ultrasonic sound to navigate where they're going, so they definitely can hear it. In fact, they not only hear ultrasonic sounds, they produce them that bounce back and come back to their heads, and they detect the ultrasonic sounds in order to locate things around them or where they're at. So the upper limit for people will get shorter and shorter as you get older. I'm older, but I also played drums for a long time, so my hearing is much, much worse than 20,000. I can hear to 8,000 if it's played loud enough. And the thing is, high-pitched sounds are going to be inaudible to older people, even though younger people might hear them. If I played a tone for you, I've got a system on here where I can play a pitch. This is 3,500 hertz. Well, you can hear that pretty easily. I can hear that pretty easily. But if you went up in frequency, so now here's about 10,000 hertz, I can hear it, but it sounds like it's barely audible to me. Some of you may hear it quite loud, and by the time we're at 20,000 hertz, I can't hear it at all, but you might be able to hear it. That's 20,000 hertz. So it's going to vary with time, with aging, and as well as your exposure to loud sound. So the intensity of sound, the intensity is an actual number we can measure with some kind of scientific instrument. And this number directly is based on the amplitude of the wave. If it was a transverse wave, it would be like this, but the compression wave of the sound. So because the compression and the rarefaction of the air in a longitudinal sound wave, it involves changes in pressure. When you compress air, you get high pressure regions followed by a rarefaction, a low pressure region. So you get high pressure, low pressure, high pressure, low pressure. So it's a pressure wave. So you'll see these plots that look like transverse waves, but they're just a graphic representation of the fact that a high level means high compression and a low level means low compression or a vacuum or a near vacuum. So the maximum sound, the loudest sound that can be heard, the highest intensity sound possible, is when all the air compresses together and none of the air is in the rarefaction. It's completely vacuum, followed by a tight packing of air, followed by no air. So it's high pressure, low pressure, high pressure, low pressure as the wave is traveling. That's the most you can get with a sound wave in terms of intensity, in terms of maximizing your crest by compressing all the air in a very tight space and then having no air and then compressing your air and having no air. That's the best you can do with sound. And as a result, there's a limit as far as how loud sound can get. When we talk about decibels, I'll explain to you later, the highest sound in decibels that is possible is about 193, 194 decibels. Beyond that, it's not possible on Earth because you only have so much air to compress and you can only make so pure a vacuum following it. Once you hit that limit, there's no bigger intensity as far as amplitude of your wave to get than that, and therefore you won't get anything louder than that. But intensity is directly proportional to the square of the amplitude. So if I have a wave that has an amplitude of this high and I double the width of the wave, the amplitude's half the width, but if we take the width and we double the width, we will increase the intensity fourfold, 2 squared. If I triple the amplitude, I will increase the intensity 9-fold. Now, that's not telling you how much louder it is. That's more complex, but it has more intensity. It's more energy per second, which we would call watts. That's what power is, energy per second, per area that it's being broadcast out. So we tend to measure intensity in terms of watts of power per area that it's striking. So the human ear has a wide range of intensities that we're able to hear. The lowest range of the lowest intensity that a human ear can hear typically is 10 to the minus 12. That's 1/trillionth of a watt per square meter. That's an incredibly low amount of power for a box that is 1 meter by 1 meter of energy coming and hitting you every second. All right, and that low a level has been assigned the title of 0 decibels. You probably heard that term. So we call 0 decibels, that is the bottom intensity that humans can hear. Anything lower than that is too quiet for anybody to hear, and we call that the threshold of hearing. But humans can also hear insanely loud sounds, and we can hear up to 1 watt per meter squared. That doesn't sound like much, but that is an enormous amount of power for this box of 1 meter by 1 meter, coming and smacking you in the face, smacking your ears. And so this is a value that's 1 trillion times the low end, 10 to the minus 12. So it's 1 trillion times. We can hear a range from something to 1 trillion times more intensity. That's what our ears are capable of doing. And that high level we call 120 decibels. So let's talk about this decibel system so it's a little more clear. It's a little complex, it's a little confusing, but I'll do my best to explain it. All right, so because the range of intensities is so incredibly huge, it's 12 powers of 10, a trillion range from 10 to the minus 12 to 1 watt per meter squared. So instead of using these huge range of numbers, we assign the bottom one, the lowest one, 10 to the minus 12, we assign that to be 0 bells, B-E-L. And this is a unit of sound intensity that was named after Alexander Graham Bell. Alexander Graham Bell invented the first patented telephone. He was extremely interested in sound, and the reason he was interested in sound in general was his father, his brother, and his grandfather were all involved in learning about speech and teaching speech and sound, and his wife and his mother were both deaf, so he had to communicate with them. So he had an enormous driving interest in learning about sound and doing something for hearing. Though obviously the telephone that was invented is best for people with hearing, but his interests ranged to helping the deaf as well. So the unit Bell is named after him, but Bell is a whole power of 10 in intensity. So if you went from 0 bell to 1 bell, that's 10 times the intensity. That would be on the bottom of this chart, going from the threshold of hearing at 10 to the minus 12 watts per meter squared, or 0 bells or 0 decibels, to the next one. Rustling of leaves is 10 times the intensity at 10 to the minus 11. So we went from 10 to the minus 12 to 10 to the minus 11, 1 power of 10. We call that 1 bell, or 10 decibels, decibel. Decibel is a deci means 1/10. So we typically measure sound intensity in terms of these units, decibels, tenths of a bell. So the idea is every 10 decibels, you're multiplying the intensity by 10. So if you add 10 to the decibels, you're multiplying 10 to the intensity. So going from 0 to 10 decibels is multiplying the intensity from minus to 10 to the minus 12 tenfold to 10 to the minus 11. So every time you add 10 decimals, it's 10 times more intense. That's the intensity of sound. And by the time you get towards the top of this, at 120 decibels, we're at 1 watt per meter squared. This is the limit of our hearing before it really hurts, and it's called the threshold of pain for obvious reasons. So that's our range of trillion times intensity that our hearing is able to detect, which works out to about 4,000 times in intensity. Every time you go up 10 decibels, it's roughly twice as loud to people, but that's totally subjective, person to person. So if you doubled every time you add 10, you double, and you double 12 times, that's about 4,000 times. So hearing an air siren is about 4,000 times as loud to you as somebody barely whispering that you could barely hear. So if you look at this, a jet airplane that you're 100 feet away from, 30 meters away from, it's a range of 100, it's about 140 decibels. That'll start damaging your hearing significantly. And 193 is the highest possible, at least in Earth's atmosphere. If you went to a place that had a denser atmosphere, you could have more air compressed and followed by a vacuum, and you could actually go to higher decibel regions. But on Earth, 193 is our limit. All right, so sound intensity is purely objective. In other words, we can have an instrument that measures the amplitude and converts that to intensity and spits out a number of watts per meter squared. That we can absolutely measure. It's an objective measure. But loudness is what we feel it sounds like, how loud it feels to us. And some ears are better than others at hearing every sound, but most ears are better at hearing certain frequencies than others. And it turns out humans in general are really good at hearing 3,500 hertz range. That's close to the top of a piano. We are really good at hearing a sound from that frequency range, even at low intensity. It just sounds louder to us, even though it might be lower intensity. And we are not so good at hearing sounds that are much lower. And I'm going to actually pull up, I bought an app recently, which is really nice. I can play the same intensity sounds at two different frequencies, so you can hear exactly what we're talking about here. So if you have a sound that's 80 decibels at 3,500 hertz, so that's near the top of the piano, that's twice as loud or more. For me, it's actually much more than the same decibel level of only 125 hertz. 125 is close to the bottom of the piano, the lowest notes on the piano. So I'm going to play for you 125 hertz and then 3,500 hertz at exactly the same intensity. It's not 80 decibels, but it's in that ballpark. So here's 125 hertz. I'll put the phone close so you can hear it. I don't know if you can even hear that. It's pretty low, and that's maximum intensity that my phone can put out. I'll put the frequency up a little higher because that'll be a little louder to you subjectively. So that's 250 hertz, still very low, not where our ears are very sensitive to. You can hear that pitch. Now listen to the exact same intensity, which should be the same loudness if we were able to detect everything with the same loudness, but we don't. Our ears favor 3,500. So here's the 250, and here's 3,500. And that is painful to listen to for any period of time. And I apologize if I disturbed anybody listening to this video. 3,500, your ears are exquisitely good at hearing 3,500 hertz. And that might be for evolutionary reasons. Hearing high-pitched screams from animals or people or somebody in danger or animals attacking is going to be beneficial to human beings and probably aided in the survival of humans. So quality. Quality is the tone of the sound, the timbre of the sound, the quote-unquote color of the sound that allows us to distinguish pitches, the same pitch, the same frequencies played by a piano versus a clarinet. We can play the same note on both and they'll have the same fundamental frequency, the same pitch to us, but they won't sound like the same total sound. And that is the characteristic we call timbre, the color of the sound, the quality of the sound. And that's due to all the different partial frequencies over partials, which are the harmonic frequencies added to the bottom frequency, the fundamental frequency. So it's that sound that adds to the musical sound besides just pitch, which is like frequency, loudness, which is like intensity, or the length of tone, how long we're playing the note. So quality is due to the superposition of many tones at the same time. We have a fundamental, which we also call the first harmonic. So here's a picture as if we're plucking a string. And when you pluck a string, the fundamental frequency, the main frequency of that string, is vibrating through the string, and it has a wavelength that is twice the length of the string. In other words, when you pluck a string, you're only seeing half of a single wave. It's either up or it's down. You're not seeing the up and down of a full wavelength. So the first harmonic is just half a wavelength. And that would be the lowest frequency because in this case, from left to right, it only happens half a time in that length of time that it vibrates across. All right. Whereas the second harmonic, you get a whole wave. So it's double the frequency and half the wavelength. The wavelength is shorter because in the first harmonic, we're only seeing half. So we'd have to go out twice as far to see what a whole wavelength looks like. It would be twice the length of the string for that first harmonic. The second harmonic, the whole wavelength fits in the length of the string. So the wavelength is half as big, but the frequency is twice as fast. In other words, we get that whole thing traveling, we get a whole wavelength traveling in the time it takes across the string. So that would be a partial, a extra harmonic beyond the first harmonic, which we call the fundamental. The lowest frequency, the first harmonic, is called the fundamental. It's the one we perceive as the overall pitch of a note. But you have all these other harmonics that are multiples. The third harmonic is 3 times the frequency of the first. The fourth harmonic is 4 times the frequency. And when you have 4 times the frequency, it's 1/4 of the wavelength. One goes up, one goes down. They're inversely proportional. And so the partials are these multiples, right? It could be 2 times, 3 times, 4 times, 5 times, 6, 7, 8, whatever. added on top, and they all will vibrate with different amplitudes. So they might not have that full bend up and bend down if it was a string, or if it was a column of air. There might be a mixture of compressions superimposed over the main compression rarefication pattern of the fundamental, and you get these complex patterns when you add them all together, and each one will contribute a different amount to the total. And that total composite, so the bottom is just an example of mixing just two harmonics. The first harmonic, which is either up or down, and the third harmonic has a wave and a half, a 1.5 wavelengths across, superimposed on it. So you have the big wave, but a little wave going through the big wave at the same time. And we would perceive that as a richer tone, the timbre of the tone, that's more complex than just the single harmonic. But our ears would say, oh, the overall frequency is whatever the frequency of the first harmonic is, the fundamental. It's the one that we feel is the strongest one to our ear and our brain. So the quality of the tone is determined by the presence and relative intensities, in other words, related to the amplitudes of each of the partials, each of the multiple harmonics, the harmonics that have multiples of frequency. So if we go back here, let's say the frequency of the first one was 100 hertz, the frequency of the second harmonic would be 200 hertz, the third one would be 300 hertz, the fourth one would be 400 hertz. So the bottom composite would be this 100 hertz that we'd hear in general, but we'd hear this wavering within it to kind of add extra quality of tone to the 100 hertz tones that we'd hear. So it's the combination of these partials, and this is what makes different instruments playing the exact same note sound different. If you look at these two notes, here's a pattern of a piano playing a C and a clarinet playing a C. And in this case, the C has a frequency that for the amount of time that we're playing it on this graph here, you see a repeated pattern 5 times for both the piano and the clarinet. So they have the same overall frequency of 5 times per whatever the total time of this graph is. I don't know what the total time is, but it's probably some fraction of a second. We saw 5 waves per whatever that time is. That would be our frequency. So they both have a same overall frequency, but if you look at the individual partials, the little waves that make up the big wave, they're different. They're different patterns. And the pair of tones of the same pitch, so the tone from the piano and the tone from the clarinet, have a different quality to them because of different combinations of the second harmonic and third harmonic and fourth harmonic added. Each one adds a different amplitude to the total wave pattern, so they end up with the same overall pattern of 5 per whatever this time is, but each one has little bumps and grooves here that give a different quality of sound to the human ear, and they make them sound like different musical instruments even when they're playing exactly the same fundamental note, the exact same bottom frequency. So musical instruments, there are a lot of ways that things vibrate to make sound ultimately in the air. So stringed instruments, you're plucking a string or you're hitting a string with a hammer. In the case of a piano, you press the key on the piano keyboard, it makes a little hammer hit the string and bounce off the string. That's why pianos are considered both a stringed instrument and a percussion instrument, because the hammer hitting means it's percussion, but you're hitting a string, so it's a stringed instrument. If you ever wondered why that is. So whenever you pluck any string or strike any string, you're going to vibrate the string, but a lot of stringed instruments are attached to something else that's going to vibrate. A violin, the strings are on the fretboard, and the fretboard's attached to the body of the violin, which will vibrate. On a piano, you pluck a piano string, it's going to vibrate the entire soundboard of the piano, and that's what creates a much louder sound than just the hitting of one string. Otherwise, we'd barely be able to hear that. So the energy is transferred from striking a string that doesn't produce that much intensity of sound to the soundboard and vibrating that, and that will vibrate the air around it, and that's what we end up hearing. So vibrations of strings will be dependent on a number of things. How long the string is, the tension on the string, how tight we're pulling it. And you can prove this to yourself by just taking a piece of string and putting one end in your teeth and holding the other one
and then plucking it and then pulling it a little tighter, and you'll hear the pitch go up because the frequency goes up. And so you put more tension, the pitch will go up. If you have longer strings, you have lower frequencies, because remember that fundamental is half a wavelength. Well, if you have a longer string, that's a longer wavelength, that's a shorter frequency. Shorter frequency, lower frequency means deeper pitch, lower pitch that we perceive. So long strings have low pitch, short strings have high pitch when we pluck them. And then how thick the string is, how massive the string is. Heavy strings will tend to vibrate with deeper notes than very thin strings. Take a look on a piano. By the time you're at the very low notes, those strings are incredibly heavy reinforced strings, very thick compared to some of the other strings that aren't that much shorter, but they're much thicker. And then the speed of sound will play a role as well. If you're at a high altitude where the air is thinner, less dense air means slightly faster speed of sound, so you'll get different variations, because remember, the wavelength times the frequency equals the speed of sound. Well, if you've got a set wavelength and you change the speed of sound because you're at high altitude or low altitude, you'll change the frequency, so it might not be the pitch that you've set for that musical instrument. So you might have to retune it if you're up high, if you're playing in Colorado versus playing in Florida where the altitude is low. All right, so aside from vibrating strings, you have directly vibrating columns of air. And there are lots of musical instruments where you're either vibrating columns of air in the musical instrument directly by blowing into them, like brass instruments, like a trumpet, a trombone, a French horn, a tuba, sousaphone. These are instruments where you're blowing air into some long tubing that's changing shape, it's changing thickness and width of the column, and you end up producing these different tones because you're vibrating the air within the musical instrument, and then that's released out the opening of the instrument, and that's what produces the sound waves that eventually reach your ear. But you also have reed instruments, the reed woodwinds. There are reed woodwinds like clarinets and saxophones and oboes and English horns. And then you have the non-reed woodwinds like flutes, fifes, and piccolos, which I'll talk about next. But with the reed woodwinds, you're blowing onto a reed. You're literally vibrating the reed directly with your mouth. That's in the mouthpiece of a clarinet or a saxophone or an oboe or a bassoon. And the reed vibrates, or in the case of oboe and bassoon, they're double reeds. They're vibrating, and those vibration of the reeds makes the air on the other side of them vibrate, and that goes through and vibrates a column of air in those musical instruments. And the column of air is varied not just by the length of the instrument, by keys. Either you're pressing with a brass instrument, or you're covering up holes in the woodwind instruments, either with keys that cover up the holes, or you're covering up directly with your fingers. And that changes the length of the pathway that the air is blowing through, and that's what changes the pitch in these musical instruments. And then fifes, flutes, and piccolos, you're blowing through a hole, so there's no reed, and you're blowing in directly like with brass instruments, but in this case, the hole is a certain shape that will make the air flutter right away from that shape and blow through, and you get the sounds that are classic of a flute and related instruments. Now, percussion instruments, specifically the drum percussion instruments, the ones that have some kind of membrane, some kind of skin over top of some drum shell. These, it's the membrane that's vibrating. It's either vibrating because you're hitting it with a hand for hand percussion, or you're hitting it with a stick or a mallet, depending on what type of percussion it is. And when you do that, the membrane will vibrate, and you'll produce waves. It'll actually be longitudinal waves that will set the air in motion around it into, it's transverse waves. I said longitudinal. It's transverse waves through the membrane. So it's actually moving up and down in waves, transverse waves, but that will set the surrounding air in motion in longitudinal waves of compressions and rarefactions of high pressure and low pressure of the air spreading away from the drum. And this tone is going to be very dependent on the size and shape of the drum, but it'll also be dependent on what the skin of the drum is made of, what the membrane is made of. And you can get drums that have synthetic heads. They might be made of nylon, and they have one very specific type of tone. Or you can get them with natural animal skins. Frequently, goat skin is one of the best for a lot of hand drums. I have a set of conga drums, and all of them have goat skins on them, and you can hear the difference between hitting a nice warm goat skin head as opposed to a higher crack from a nylon head. So I always favor the natural skins for that. But you'll get very different tone because of the elasticity of that material that makes up the head, the skin of the head, the skin, the membrane. They're all different words for the same thing of the drum. How much tension you put, and you can tighten up the tension either with little nuts around the drum or occasionally with strings that tighten it up, or just using your hand, one hand to press the drum to basically make the head stiffer, and then when you hit it with the other hand, you'll get a higher pitch. You can even get kind of a cracking sound from hitting it just right. So you can vary the pitch tremendously on drums by playing around with tension, the type of head, the elasticity of the head, and the shape of the drum, the size of the drum. Smaller drums will have higher pitch than larger drums. So there are a lot of ways to vary it. But those drum heads are moving with transverse waves, and they're vibrating the air around it that turns into longitudinal sound waves. And the pitch will be generated from these changes in tension in the head, and then you'll hear the sound waves, these compression waves that as they hit your ear. All right. So there's another category of musical instrument, the electronic musical instruments. And the first one was invented by Robert Moog in 1964, and it was called the Moog synthesizer. And it was very popular with musicians back in the 60s because it was a way of making synthetic music without your typical blowing an instrument into an instrument or hitting an instrument or using reeds or whatever. You essentially are playing it like a keyboard instrument, but instead of hammers striking strings in a piano or a harpsichord, you have circuits that you're completing by playing with your hands on the keyboard, and that completes circuits, and those circuits will generate certain wave patterns that are transferred to a speaker that will generate actual physical sound in the air. And this requires knowledge. It definitely required advanced knowledge originally in the electronics and acoustics when these instruments first came out. Now they're much more user-friendly and pretty much anyone can use them. But if you're really into electronic music, you really need to understand a lot in order to compose music or play music if you want to get the most out of this extreme form of technology for producing electronic music in order to combine the advanced acoustic knowledge with the advanced musicology knowledge. So let's talk about Fourier transform. Fourier transform was invented, it's a mathematical process, but before we talk about what that is, let me give you a little background on why this is important or what even led to it. So if we look at the sound of a single musical instrument, it's still going to be complex. They're going to be changing notes. They're going to have all these harmonics, these partials over top of the fundamental frequency, and they're going to add together to give this quality of sound. Plus, the instrument's going to be changing notes constantly with different rhythms and different frequencies. So you'll get this complex pattern. So here it is for an oboe. And then right below that is for a clarinet. And they may be playing the same song, but different notes for the same song, different parts of the song. So they're not going to have the same pattern. Plus, they're different musical instruments, so they have different harmonics, different partial tones layering on top of each other to get different composite waveforms. But if you add those together, they each have their own composite waveform. You add those composite waveforms, you get an even more complex waveform shown in figure C. And you can see all the features of both of those mixed in. You see the peaks from the oboe, the 3 big peaks from the oboe are still represented in the composite, and the 5 big peaks from the clarinet are still represented in the composite. It's just a little hard to see the individual pieces, but it's a more complex pattern. Now, what Fourier did was he thought about this, and he said, now he didn't have an oscilloscope to look at this. He was thinking about waves in general, and he thought, what if I can go backwards? What if I can take any pattern that's repeating in any way, no matter how complex, and figure out what all the individual waveforms are that make it up? Not just the oboe, but all the pieces of the oboe and all the pieces of the clarinet that add to it, and break it down. So Jean-Baptiste Joseph Fourier was French. He was a French mathematician living in the late 1700s, early 1800s, and he figured out that if something has any kind of mathematical regularity, it could be music, but he wasn't necessarily thinking about music, but he was thinking about these complex wave patterns. And he realized that no matter how complex this pattern is, he could break it up into a collection of a large number, if necessary, a large number of very simple repeating sine waves that have one frequency and have one amplitude, so they're only going from here to here, and half of that width is the amplitude. And maybe you have 3 or 5 or 20 of these that will all add up to make some complex pattern that is actually generated mathematically and acoustically. And he realized that if you analyze the math in a certain way that he invented, you could break these down into their constituent simple sine waves. And they each have their own frequency, and they each have their own amplitude. So it's just a simple sine wave and another simple sine wave with a different amplitude and different frequency, and another one with a different amplitude and different frequency. And if you add enough of these together, you will get the one you started with. And he worked out how to do this mathematically, and this is called Fourier analysis. Most people call it Fourier transform or Fourier transform analysis. So the idea is if the actual tones that are being produced, if you have this fundamental, so here's your wide wave, your lowest frequency with the biggest wavelengths, that's your fundamental. But when you play a musical instrument, you're going to have second harmonic, third harmonic, fourth harmonic, because some of the air or whatever is vibrating will vibrate at twice the frequency or 3 times the frequency on top of the ones that are vibrating at the original frequency. So you end up with this fundamental, that's the lowest frequency, the fundamental, also known as the first harmonic, and that's what we hear as pitch. That's what we think is what we're hearing as pitch. But we'll hear these other sounds that are superimposed on it. So if you look at the second harmonic, you'll notice, if you look at the fundamental, you see one wave for every line that I put in. I just put these lines in. So you'll notice there's a repeating pattern. Every line, there's one whole wave. But if you look at the second harmonic, you get 2 whole waves every line. So it's twice the frequency and half the wavelength. The third harmonic, you get 3 of those waves for every time line that I put in, and it's a third of the wavelength of the fundamental. Well, you'll also notice that in this particular example, the amplitude of the second harmonic is much less than the amplitude of the fundamental. Fundamental is pretty wide, the second harmonic's narrow, and the third harmonic's even narrower. And it doesn't have to be this way. Usually the fundamental is the biggest, but the others can be a variety of combinations. But when you add these together, if you actually mathematically said, okay, what level is this on this part of the wave at this time, and what level is this and this one, and you added up 3 points each one as you go across and add them together, you get this composite wave. But if you look at this composite wave, yes, it's complex, but you'll notice the repeating pattern is still one complex repeating pattern every line, just like the fundamental. And this is why we hear it as the frequency of the fundamental more than anything else. And this is why when we hear pitch, it's the pitch related to the fundamental, not necessarily to the second, third, or fourth harmonic. It's because the overall pattern still matches the original frequency of 1 per line in this particular example. So we've summed up these waveforms. And Fourier analysis could look at this bottom one, do an analysis, and now this is done with computers, and it could quickly calculate, oh, this wave, this composite wave is made of this much fundamental with this amplitude, this much of the second with this much amplitude, this much of the third harmonic with this amplitude, and when I add them together, I'll get this form. Boom, I've done the analysis. I've broken it down into individual pieces. And this is extremely useful for reproducing sounds because it's very easy to generate individual sine waves. It's harder to produce these composites. But if you know what all the pieces are, that becomes trivial to generate each of those frequencies and each of those amplitudes. So let's talk about digital information here. Digital versatile discs, DVDs, and compact discs, DVDs. Digital versatile discs, DVDs, and compact discs, CDs. These are ways of taking
what we call analog information and turning it into digital information. And I'll talk about what that means. So a phonograph, the old vinyl records, where you put it on and there's a needle on top of it, and the needle is bouncing up and down inside little grooves that have been carved in your vinyl record. And depending on the height that it's at, you will get different tones being produced that come out of your speakers, and you hear the music or spoken word or whatever is coming out. Well, because the needle can go within a certain range, could be any height within there, right? It's not that it can only be certain heights in there and little steps. It can be anywhere in there. It can be any value from the top of this amplitude to the bottom of this graph here to the bottom trough. It can be any value in theory, and we refer to that as this continuous version where the signal could be any value between something and something. That's called an analog signal. It could be anything. It's any number of values between there. If we were able to measure closely enough, we could get every individual value from one point to the next point. But a digital device is different. Digital devices, the signals that come out of a digital device or the signals that are read by a digital device can only be very specific levels. So think of it this way. They're old bathroom scales where you step on it and you watch the numbers rotate and the needle's there, and you look down and you say, okay, what's my weight? And you see, oh, it's between 153 pounds and 154 pounds. And, okay, it could be 153.175 if I was able to measure carefully enough. It could be 53.176 or 53.237. If you were able to see between there close enough and you had an accurate enough, wide enough space, you could conceivably measure any weight in there, any continuous value in there. But a digital scale, it sets it at very specific digits. And so you step on a scale, you're either 151.2, 151.3, 151.4. There's nothing in between. It has to be this level, or this level, or this level, or this level. It can't be in between levels. And so it's digitized. That's what we mean when we say it's digitized. It has to be a specific digit, nothing in between. And that's the difference between an analog measurement and a digital measurement. The old thermometers where you read the mercury or the alcohol in the thermometer could be theoretically any value. Those are analog measurements. A ruler is an analog measurement. In theory, if your eyes were good enough and your lines were sharp enough, you could measure any value between, it could be between a quarter and the next quarter, or between an eighth and the next eighth. But in digital, it's every specific value, and they're very specific intervals. Maybe it's every eighth or every 16th, or in the case of digital, it's usually every 10th or every 100th or every millionth or whatever you're doing it in digits. But the point is, it can't be any value. It has to be very specific values. Well, how do you convert an analog signal into a digital signal? An analog signal can be anything in this black curve here, where we have analog signal versus time. So you have to have a converter that will convert analog to digital. They're actually called A to D devices, analog to digital devices. And they have inverse devices as well. But the device would basically say, oh, the signal's here? Well, that's close to this digit, 51.2. Oh, you have a signal here? Well, that one's close to 51.3, and this one's close to 51.4. Whichever one it's close to, it'll set that value. So when digital music first came out, I guess the late 70s, early 80s, when CDs were first coming out, there were so many levels that sound could be at, and as a result, there were some audiophiles, some experts in stereo equipment and listening to music that claimed they were able to help tell the difference between digital versions of music and audio and analog versions of music from say a vinyl album. And that may or may not have been true, but eventually they got those intervals smaller and smaller so that nobody can hear the difference. And the quality is very, very good with digital music devices nowadays. And then of course now we switch to MPEGs and the MP3 and various other technologies for saving and sharing electronic versions of music that was originally recorded analog in an analog fashion by live instruments. So this is the advent of the digital age in terms of turning analog information into digital information, and you can do this with signals for anything. It doesn't have to be for music. It could be for any instrument that's collecting information to be converted into digital format. So DVDs, the way DVDs work, and there's some variations depending on the version of DVD, but the idea is everything is in zeros and ones, because zeros and ones are the language of machine language in computers. That's the binary language. And the way these disks create that information or store that information is the disks themselves have microscopic pits in them. So the surface is coated, the surface of the disk is coated with some reflecting material that when a laser hits it, it'll reflect back, and the device will go, oh, I see the laser I just shined. We'll call that a 1. I got the reflection. It's positive. It's a 1. Okay? But the pits that are carved in it, and usually carved in by lasers in manufacturing, the pits don't have any coating in the bottom. So when the light hits the pits, the light is just absorbed at the bottom. It's not reflected back to the detector. And the instrument goes, okay, I shined a light in here. Nothing came back. We'll call that a 0. And so if you might have a long pit that's a 0, 0, 0, 0 until you come to the part where it's not a pit, the high level of the surface, the coated surface, 1, 1, 1 until you get to a pit, 0, maybe it comes back up, 1. And so every time there's a pit, it's a 0. Every time you're at the top surface, it's a 1. So you got zeros and ones in whatever pattern. And that information is converted as binary code by some machine language that will interpret that into information. And that could be music information, it could be movie information, it could be computer information, numeric information, whatever you want. Any kind of information can ultimately be stored in the form of binary code, and it can be stored in these DVD discs by carving different pits in there in different patterns. And so we'll stop right here.